Hello everyone, welcome back to ptet.chemistry channel. This is Mr. On. In this video, I'll cover the idea on reacting volumes of gases. So this is the first of a two-parter series on these reacting volumes of gases. So usually when we talk about gases, we associate the molar volume of gas at RTP, that's room temperature and pressure. We have 24 dm cube per mole of any gas, all right? And that's also equal to 24,000 dm cube per mole of any gas. And we know that when we want to find the mole of a gas, so the mole of a gas is equal to the volume of the gas divided by the molar volume, because the volume of the gas would be either in dm cube or cm cube. When you divide by molar volume, which is in dm cube per mole, then dm cube divided by dm cube per mole will give you mole as the unit. If you use cm cube as your volume, then you will have cm cube divided by cm cube per mole, which will also give you mole as the unit. So the good thing about gases is that because when we are dealing with examples like this, here we have combustion analysis. So we talk about working out the amount of CO2 by reacting it with an alkali. So alkali or base reacts with acidic CO2. So when your combustion produces CO2, you want to find out how much CO2 has been given off. You can react it with alkali like KOH, which is potassium hydroxide, K plus and OH minus, or NaOH. They behave in similar way. They react with an acidic oxide in a neutralization reaction. Acid plus alkali, acid plus base. Alright? Okay, I mean alkali or base, they are both essentially the same, yeah? So in this question, you have a mixture. You have a mixture of methane and ethane. So we need to be careful here. There's probably an easy way, and there's probably a hard way. I'll go through the more I wouldn't say easy, I wouldn't say hard, but like the more obvious way where you do one by one, okay? So the excess oxygen, that means not all the oxygen is reacted. That means all of these are reacted. They are what we call limiting because the oxygen is in excess, all right? If I write the balance equation, CH4 plus O2 will give me CO2 plus H2O. One carbon there, give me one carbon, 4 hydrogen, so I need 2 H2O because 2 times 2 will give me 4 hydrogen. The oxygen then is O2 which is O4. I need 4 oxygen, sorry, not O4 but 4 oxygen atoms, so I need 4 oxygen atoms, so I put a 2 there. If I have ethane, which is C2H6 from your GCSE or your O-level or whatever, when you balance, when you get the alkane formula, it's CnH2n plus 2, right? So CO2 plus H2O, you will get 2 CO2 because there are 2 carbon here. There's 6 hydrogen. To get 6 hydrogen altogether, I need 3 there. 3 times 2 is 6. 2 times 2 is 4. 3 times 1 is 3. So altogether, I got 7 oxygen atoms. To get 7 here, many people don't like fractions, okay? 7 over 2 times 2 equal to 7. I have 7 oxygen atoms here. But I started from O2. That's why I can use the fraction, all right? In these kind of calculations, I would advise you to always keep the hydrocarbon as a 1 and 1 in front, because if you make this into a whole number, you have 2 in front, and the higher the mole ratio there, the more complicated the calculation will become because the numbers quickly multiply up, yeah? So if I combine these two equations together, so methane and ethane do not react together necessarily. So what you get essentially is 2 plus 3.5, which is 5.5, so that is 11 over 2. And then you will give off 3 CO2 total and 5 H2O. This is obtained from this plus this. Okay, so what do we know? Okay, we're talking about reacting volume at start. Why are we talking about reacting volume instead of reacting mole? Because if these are gas, this is a gas, which is an excess, which we don't need. These are gas. Because they are all gases, their volume ratio is the same as the mole ratio. Because all of them, the gas the gas, they have the same molar volume at room temperature and pressure, which is a constant, right? 24 dm³ per mole, or 24,000 dm³ per mole. Okay, so therefore the volume ratio of the gas, okay, this is an excess, so perhaps we shouldn't use it. The volume ratio of the gas is going to be equal to the mole of the gas. That's why I'm talking about volume ratio. Okay, this only applies to gases, yeah, not solution, not solid, not liquid. Alright, so volume at start, I have 10 cm³, I have 10 cm³. Alright, the oxygen is in excess anyway. So the volume at the end, well, if I combine the equation correctly, but if I look at it individually, 1 mole of this will give me 1 mole of that. 10 cm³ will give me 10 cm³ because 1 mole give you 1 mole. 1 cm³ will give you 1 cm³. Based on what I said, they are related by the same molar volume at room temperature and pressure. So mole ratio is the same as volume ratio. Mole ratio 1:1 is the same as volume ratio. 1 mole of 1 cm³ of this will give you 1 cm³ of that. 10 cm³ of this will give you 10 cm³ of that. 10 cm³ of this will give you 20 cm³ of it. I've combined the equations together. So 1 mole of this give you 3 mole of it. Well, because I've combined them together now, alright? Balanced, obviously. So obviously now, if I have 10 cm³ that reacts, I will get 30 cm³ at the end. I'll get 0 and 0 because they are limiting. Completely used up. Completely used up. Okay? And then you still have excess oxygen. But I don't know the volume because I'm not given. Alright? They're asking for what volume of gas was absorbed by the alkali. And we know it's just the CO2 that's being absorbed. And 30 cm³ of CO2 has been produced. Therefore, 30 cm³ of CO2 was absorbed by the alkali or the base, whether it's KOH or NaOH. Alright? So I hope you get to see the idea of working out the volume at start and volume at end. That's the same as working out the mole ratio because we are talking about gases. Alright? That's the important idea here. And obviously CO2 being an acidic gas, it will react with the alkali in an acid-base neutralization reaction. This is a further question of that application. So we are going to work out the formula of the hydrocarbon. Okay, so this is actually a multiple choice question from the Cambridge International Curriculum, but it could very well be, if without this option, they could ask you in a structure questions, and it could easily come out as in any of the UK examination body, in any of the A-level exams. Yeah. Okay, so there is a general equation that some people might not have heard of or seen before. This is the general equation. It's already balanced for combustion, for complete combustion of a hydrocarbon. CXHY plus O2 will give you CO2 plus H2O. This comes down to what I said earlier about how I balance the equation. If I have 1 mole here, X mole of carbon will give me X mole of carbon. Therefore, I'll have X CO2. I have HY there, I have Y number of hydrogen atom. So I need Y over 2 times 2 because I cannot change the number there. That will give me Y number of hydrogen atoms that will balance here. So that's why this is Y over 2. And then you work out the mole of the oxygen. How many oxygen atoms would you have? Altogether, you will have 2x and you will have Y over 2 oxygen. So 2x plus Y over 2, okay? And then you need to divide that by 2 because you have an O2. When you divide that by 2, you're going to get x plus y over 4. And that is how you get this general equation. Basically comes down to balancing equations using algebra. Alright? And this equation is valid. This equation is valid when this is 1. Alright? So this is how we can find the formula of the hydrocarbon by using this general equation, which we could get by balancing each and every one of them just now by the same idea and principle. It's just using a little bit of algebra now. Okay, so what do we have? I always label my stuff on the side. So volume at the start. Remember, volume ratio of gases is the same as mole ratio of gases. Okay, so we need to work along that line here. So I have 10 cm³ of the hydrocarbon. I burn in 70 cm³, which is in excess. So the oxygen is always an excess for combustion because you want to combust it completely, yeah? So the volume at the end. The volume at the end contains 30 cm3 of carbon dioxide and 20 cm3 of unreacted oxygen. 20 cm3 unreacted. So how much oxygen actually reacts? So that's the question, yeah? How much oxygen actually reacts? Anyway, think about it. You will have 0 CXHY at the end because this is an excess. So all of this will be completely reacted. Alright? So 50 cm3 oxygen reacted. You put in 70 cm3, but you still have 20 cm3 unreacted. So 50 cm3 has reacted there. Okay? So what do I know? So that's 30. So the volume reacted is 10, 50, and 30. Okay, this is reacted. What is reacted give you whatever is formed. Sorry, that is formed. Whatever is reacted give you whatever that is formed. Alright? So what can I tell? I can complete the simplest volume ratio, which is the same as the mole ratio. That's going to give me 1:5:3. This has to be whatever that has reacted for it to work. If you simply put 70, it's not going to work because 70, not all of them reacted. Only 50 cm3 reacted because you still have 20 cm3 unreacted. Okay, this equation refers to whatever that has reacted. This equation refers to whatever that has formed. I don't work this one out because H2O under standard conditions is a liquid. So only these, and these are gas. Alright. So what do I know? So I know x is equal to 3. How do I know x is equal to 3? Because when this is 1, it's not 10. When it's 1, that's why I need to make it into 1. Okay. Then x must be 3. Volume ratio is equal to mole ratio only when that is 1 and 1, not when it's 10. Okay. So x equal to 3. So this is like your maths comparing coefficient, yeah? So x plus y over 4 for the oxygen is equal to 5. So y over 4 equal to 5 minus 3, which is 2. Therefore y is equal to 8. So C3H8. That is the one you're looking for. Even if it is not a multiple choice question, it could very easily be a structured question where you're supposed to work along that line where they might guide you, you know, how much of it has been absorbed by alkali. There will be the CM, the carbon dioxide, yeah? It's all about the volume ratio of a gas is the same as the mole ratio of the gas. In this balance equation, this mole ratio refers to what has reacted, not what is unreacted, but what has reacted. That is the important idea here, yeah? For question 3, so again, they give you a hydrocarbon. So I'm going to just use the general formula because I'm not sure what they're going to ask here. So this general formula is not obtained by magic. It's obtained by your normal balancing of equations, yeah? Just using algebra. So what do I know? I know I have mole of CO2 is the mass over the MR. So because I'm given the mass, so the MR of CO2 is 12 plus 16 times 2 is 44.0 from my periodic table. The MR of H2O is 1.0 times 2 plus 16.0 is 18.0 from my periodic table. Your periodic table might show you as whole numbers, so just use whatever is on your periodic table, I guess. So I can work out the mole. And because if I have the mole, if I have the actual mole, then these are actual mole. Can you see that? These are actual mole. So if I have CXHY, compare that mole ratio, yeah, we're comparing mole ratio to CO2 to H2O. I have 1 is to x is to y over 2. These are from the balance equation. And then I have the actual value, which is 0.200 is to 0.80 is to 0.80. These are from the calculated values, all right? Simplest ratio, so divided by the simplest number. So that means 0.200 divided by 0.200, 0.80 divided by 0.2, 0.80 divided by 0.2. So I just decide not to write the 0.00 anymore, yeah, 0.200 anymore. So 1 is to 4 is to 4. So I hope you can see now there is 1 and 1, therefore I can compare. because now I made this into 1 and no longer 0.200, just like in the previous example. Okay, so I'm moving on to the left because I ran out of space there. So x is equal to 4, y over 2 equal to 4, y is 8. So C4, H8 is what you want. Here we are working with mole. We are not working with volume because we're given the mass. If we know the mole, we can compare the mole ratio based on this equation, which balance out. And then we can work out by making it into 1 for the hydrocarbon, because only when it's 1, these coefficients can match, only when it's 1 for the hydrocarbon, because this equation is for 1 mole of CXHY. Okay, so that's the end of this first video of a two-parter series on reacting volumes of gases. So catch the next video, the second part of the two-parter series, for more complicated and advanced examples of how I use these concepts of reacting volumes of gases in mole calculations. I'll see you in the next video. Please subscribe if you haven't, and please share the words to your friends or your students or colleagues if you think these videos are beneficial, so that it can benefit more people. Thank you for watching.